Okay, Chemistry 3111. This is the second lecture on amino acids, peptides, and proteins. And we're going to start by looking at question 25.17. It says, identify the reagents necessary to make each of the following amino acids using a Strecker synthesis. So the way that you want to approach these kind of problems, the Strecker synthesis problems, is by thinking about the problem in terms of retrosynthesis. So if we draw the structure of methionine, and again, I don't ask you to memorize the structure of any of the amino acids. I would give you, I'd give you the structure of methionine. There we go. So here's methionine. And of course, we're not going to produce a chiral compound using Strecker synthesis. We end up with a racemic mixture. But what you want to think about is you want to look at how many carbons are going to be in the aldehyde that's required as my starting material, because Strecker synthesis always starts with an aldehyde. And so all of this part of the molecule here that I'm circling in red, okay, that is going to come from the aldehyde. And so your aldehyde, your starting aldehyde, is going to have methyl, the sulfur, 2 methylenes. And then you're going to have your aldehyde, like that. So what you're going to do in the first step is you're going to treat it with ammonium chloride, and sodium cyanide. And notice that you're going to have to add this carbon here, right? This carbon with the carboxylate, or the carboxyl group, is what you're going to end up with because you treat it with acid in the end. But that carbon comes from the nitrile, okay, or the cyanide, I guess, what I should say. Anyhow, it comes from the cyanide, which becomes a nitrile when you produce the alpha amino nitrile. So let's draw the alpha amino nitrile that would be formed. So we have that carbon. We're going to have our nitrile here. We'll have our amino group here. Here's the hydrogen from our aldehyde. So we have 2CH2, then we have a sulfur, and then our methyl from our methionine. And then the last step is to hydrolyze the nitrile with acid, and we heat that up. It's a reaction that we looked at in the carboxylic acids chapter. And then what you end up with is your final product, which again is a racemic mixture. And since you did the last step in acid, you're going to end up with the protonated amine, and you're also going to end up with the carboxyl group intact, like that. So that's the Strecker synthesis of methionine. Let's try one more. And why don't we try histidine? So histidine has a heterocycle in it, and we'll draw the structure of histidine. So let's draw histidine over here. Then we have a methylene. And then, sorry, I'm going to draw it a different way. I was just getting ahead of myself. I'll light, just to make things simpler. I'm going to draw it the same way it's shown in your textbook, okay? So we're going to end up making this molecule, the histidine. So we have our NH here, and then we have our nitrogen here, like this. And there we go. So there's our histidine, and we want to take the exact same approach, right? This is the part that's going to come from the aldehyde, all of this part here. And then this carbon is going to come from the cyanide, from the sodium cyanide, which then becomes a nitrile, which then gets hydrolyzed. So all we have to do is draw out the starting aldehyde. We could even take this part here and just select it. I'll see if that works. So I'll copy. I'll try and paste this, see if it works. So we'll take this, and then we'll delete the parts we don't need. There we go. All right. And so our starting aldehyde is going to look like this. Oops, there we go. I'll draw the aldehyde like that. Okay. And then the first step is you're going to treat it with ammonium chloride, ionic solid, and sodium cyanide, which you have to be careful with, of course. Then you form the alpha amino nitrile. So let's draw that out. Amino group. Here's our nitrile. Here's the hydrogen from what was our aldehydic hydrogen. And now we'll draw the heterocycle. Like that. And then we're just going to hydrolyze that, right? We're going to hydrolyze the nitrile, but since we're in acid, we are going to end up with the carboxyl intact, and we're going to end up with the protonated form of the amine. And again, this is a racemic synthesis. We don't get the just the L amino acid or just the D amino acid. We only get a mixture here, which probably wouldn't be easy to separate, but that's not the point. And there we have it. And so we end up with histidine. We can take the exact same approach for phenylalanine. I'll just kind of skip this one, but for phenylalanine, you'd want to start out with an aromatic ring like this, and then you'd want to have this as your starting aldehyde. So it might be a good idea for you to practice drawing the intermediate, right? These intermediates here, these are called alpha amino nitriles, okay? And then those get hydrolyzed. All right, well, let's move on. Let's try another problem. This one is in the exact same vein as the last one. It's still dealing with Strecker synthesis. It says each of the following aldehydes was converted into an alpha aminonitrile, followed by hydrolysis to produce an amino acid, right? That's what we just looked at in the last problem. So this is Strecker synthesis, all right? In each case, draw and name the amino acid that was produced. Well, let's start by drawing acetaldehyde. This is an aldehyde you should know full well. I asked you to memorize the common name of ethanol way back in the aldehydes and ketones chapter. So we're going to take this and we're going to treat it with ammonium chloride and, of course, sodium cyanide. I want to be careful with sodium cyanide. It's very dangerous. Anyhow, and we make an alpha amino nitrile, and then we're going to hydrolyze that nitrile in acid, and we'll heat that up, right? And we're going to convert this into a carboxyl group. So what's the R group in our molecule? Right, our R group is going to be this portion right here. This is our R group. Okay, and if our R group is just a methyl, you hopefully, recognize a couple of the amino acids that I don't expect you to memorize all of them, but it might be wise to know a couple. And when we just have a methyl group like that, that's an alanine. Alanine. All right. The next one, we're starting with 3-methylbutanol. So you should be able to draw this compound. So if we have butanol, so it's 1, 2, 3, 4, and then 1, 2, 3, we put a methyl group here. So right away, you can see the R group. If we follow the same rationale with acetaldehyde, this is our R group. And here is our R group here. So it's an isobutyl group. So that's going to produce a leucine, isn't it? All right, so let's do the exact same thing again. Treat it with ammonium chloride and sodium cyanide. Oops. Getting ahead of myself here. Come on. Oops. Where was I? Sodium cyanide. And we produce the alpha aminonitrile. So let's draw that guy. Looks like this. So we have our amino group. We have our nitrile like this. And then we're just going to hydrolyze that in aqueous acid. And we probably heat that up to reflux, for a few hours or something. And then we end up with the protonated amine and the carboxyl. And when we have an isobutyl, we get leucine. Anyhow, same rationale is applied to the last problem, which is 2-methylpropanol. So you should be able to draw propanol. It looks like this. And if we have a 2-methyl, well, you can see that the R group is right here. And so that would produce a valine. Okay, let's try another one. This is 25.19. Lots of practice here. It says identify the starting alkene necessary to make each of the following amino acids using asymmetric catalytic hydrogenation. I told you don't have to write out the whole name of the asymmetric catalyst for this. If you just write, H2, so hydrogen and chiral catalyst, that works perfectly well for me. And so again, if we think about an L-alanine, so if you look up in your textbook, if you look up the structure of L-alanine, it'll look something like this. I'm going to draw it at physiological pH. So we have the Zwitter ion. Okay, now if we want to make that amino acid, well, what are we going to start from? Right. Well, this is just a matter of memorizing kind of how or what the molecule will look like prior to hydrogenation. And the idea is that this carbon here is the one that's going to take on a hydrogen, so it must have a double bond associated with it, right? So the double bond is going to be to the methyl group. Then we don't have a chiral center here, and so we're going to have something that looks like this. And then we have an acetyl group on the nitrogen. So the first step in asymmetric catalytic hydrogenation is to treat it with hydrogen and the chiral catalyst, okay, which is a binap complex to a ruthenium. Anyhow, I told you don't have to have that memorized. Anyhow, so we do the catalytic hydrogenation, right? The chiral catalyst, if you were to just treat this molecule with H2 and palladium or platinum or nickel, you would get a mixture, right? You would get a racemic mixture because the hydrogen could add to either the top face or the bottom face of that sp2 hybridized carbon. But chiral catalysis enables us to put the hydrogen solely in the back. And then the last two steps are going to be hydrolysis, removal of the acetyl group, and then we're going to treat that with acid to protonate. So first step is sodium hydroxide. That removes the acetyl group. And then in the second step, we're going to treat that with aqueous acid, and that will give us the carboxyl, and it'll give us the protonated amine like that. And there we go. We have a chiral synthesis of alanine. We could apply the same rationale to valine. So if I draw a valine molecule, so here's valine. I'll draw it as the zwitterion. And again, I like to think of these in terms of retrosynthesis. So I always start by drawing my desired product or some variation of it, right? This is the product at a different pH because obviously you're going to isolate it in low pH. But again, we have to have a double bond to that carbon that's going to end up being our chiral carbon. We need an acetyl group on the nitrogen. We have our carboxyl, and then we're going to have our two methyl groups coming off of here, right? So the first step is going to be hydrogenation using a chiral catalyst, okay, which you purchase from some kind of supplier for, a few bucks. There you go. And you do the catalytic hydrogenation. You rejoice because you make only one enantiomer, so you end up with the S configuration at the chiral center. And we're going to treat that with sodium hydroxide. And then in the last step, we'll treat it with acid. And there we go. We're going to end up with our valine. And of course, since we're isolating it in acid, our carboxyl will be the protonated form. And we're going to have the protonated form of the amine because an amine is a base. And we're an acid. Again, you can take the same rationale with leucine. I'll let you guys try that one yourself. And let's move on to the structure of peptides. So this is section 25.4. It says here, this interesting molecule shown down here with these three green boxes, this is called glutathione. Sometimes it's abbreviated GSH, okay? Glutathione is an example of a tripeptide. But the thing is, glutathione is made of 3 amino acids. It's made from glutamic acid, cysteine, and glycine. But what's important here is that it's not just enough to mix these 3 amino acids, right, to make glutathione. They have to be assembled in the correct order. So they are assembled in this order that I have my glutamic acid followed by my cysteine and then followed by my glycine. They have to be in that specific order. If, for example, and you don't have to write this down, if you were to put, say cysteine and then glutamic acid and then glycine like that, okay, that's not going to be the same compound, is it? It's going to be a constitutional isomer, but it's not the same compound. And so the order in which amino acids are linked together to make a peptide is important. That's what we call primary structure. If any of you have taken biology and have learned or have heard about primary, secondary, tertiary, and quaternary structure of proteins, this would actually be considered primary structure, just the order the amino acids are linked together. Here's another example. Okay, say you want to make a dipeptide. You're linking 2 amino acids together. Say you want to make a dipeptide from alanine and glycine. Okay, you can't just mix alanine and glycine and form an amide bond between the carboxyl and the amino group. Now, obviously you can make that bond, but the problem is you end up with a mixture, right? If you have the carboxyl of the alanine linked to the amine of glycine to make this compound, or if you have the carboxyl of glycine linked to the amine of alanine to make this compound, these are 2 different compounds, aren't they? Okay, these are different. We'll put here different, right? They're constitutional isomers, They're constitutional isomers, but they are not the same. They're not the same compound, are they? Well, that's interesting. Okay, well, before we talk about how we would make one of those dipeptides preferentially over the other, let's talk a little bit more about the structure of peptides. So it says here peptides, and this goes for proteins as well, have an N terminus and a C terminus. Depending on the book, you might hear it called an N terminal or a C terminal, but I cut my teeth on N terminus and C terminus, so I'll always call it that. So we have an N terminus and a C terminus, and the N terminus refers to the amino group on the amino acid residue or portion that's written on the left-hand side, and that's a convention. Okay, that amino acids, when they're linked together to form peptides and proteins, if we want to write them out in a chain, they're always written like this. Okay, you see you have nitrogen, carbon, carbon, then another nitrogen, carbon, carbon, another nitrogen, carbon, carbon, another nitrogen, carbon, carbon, so on and so forth. They are always written like this, NCC, NCC, like that. And again, it is a convention that the nitrogen on the far left-hand side is called the N terminus, and the carbon over here on the far right-hand side, that's called the C terminus. So let's color code that, the N terminus and the C terminus. Again, it is a convention. So if I was to ask you to say draw or a tripeptide, you always start with the N terminus on the left-hand side. Now, as I told you last lecture, biochemists tend to steer away from using the full names of the amino acids because they're lengthy, right? It takes a long time to write those out. So instead of using the full names of amino acids, they like to use abbreviations like alanine, so they use ALA, glycine, cysteine, tryptophan, glutamine, right? So on and so forth. They have these shorthand 3-letter abbreviations. If you enroll in biochemistry at UCCS, you'll be asked to memorize those, and you'll also be asked to memorize the 1-letter abbreviations. But what do we know? If you open up a textbook and you see a bunch of amino acids linked together like this, going from left to right, you know that the N terminus is going to be on this side, right? There's going to be an NH2 here, right? And this is going to end with a carboxyl, like that. Okay, again, it's a convention, N terminus and C terminus. A little bit more about peptide bonds, because we know that amino acids, when they're linked together, okay, NCC, NCC, right? What I just called, or what I referred to as primary structure, we know that peptide bonds that link the amino acids together are nothing more than amide bonds. And we've spent some time talking about amide bonds, haven't we? And in fact, we looked at this way back in chapter 1, no kidding, of Organic Chemistry 1. And we said, what's the hybridization of this nitrogen here in an amide? Well, if you look at it, right, you'd say, well, it's got 4 regions of electron density. It's got 3 sigma bonds and a lone pair. So it's sp3 hybridized, but in fact, it's not. It's sp2 hybridized, as is shown here. If you look at the resonance structures of an amide, you can see that there's a partial double bond character. And on account of that partial double bond character, it restricts the rotation around this carbon-nitrogen bond. So this carbon-nitrogen bond has a restricted rotation. It's not that it can't rotate, but it's highly restricted. Okay. In fact, if you look at the 2 conformations of that bond, of that carbon-nitrogen bond, and I'm talking about this bond here, okay, that's the bond of interest on this slide, okay, it can exist as either S-trans or S-cis. Now, if you don't remember what the S stands for, that's nothing more than sigma, okay? You're used to trans and cis in double bonds, right? If we see something like this, we would say that's trans to butene, and we'd say this is cis to butene, right? That cis and trans is referring to an olefin, an alkene. When we have trans and cis, but we're dealing with what looks like a single bond, okay, we call that S-trans and S-cis, because remember, it's not a double bond, but it has double bond character. And again, because of that high barrier of rotation, which is around 80 kilojoules per mole, the S-trans is going to predominate. And hopefully that's, should be intuitive for you, that this will be the lower energy conformation. And it's simply based on sterics, right? Those 2 big gray ovals, if you will, or the rest of the molecule, on either side of that amide bond is going to have less steric hindrance in the S-trans conformation. Now you might be wondering, okay, well, what's the fallout of all this? What's the result of this high barrier of rotation for all these carbon-nitrogen bonds that you find in amide linkages that are found in peptides or proteins? Well, because those bonds have a preference for the S-trans conformation, what it does is it provides some rigidity to the structure of a peptide or a protein. And it's going to be very important when you look at the actual conformation of a protein, when you look at its three-dimensional structure. Now, again, the other backbone bonds, so the ones that aren't highlighted in green here, they can freely rotate, no problem. So we can have a variety of conformations for those bonds, but again, the ones that are highlighted in green experience a restricted rotation. Another thing that's interesting with respect to the structure of peptides and proteins is the formation of a disulfide bridge. Anybody who's learning about the organic chemistry of proteins, or even if you're just taking a biochemistry, you have to know what a disulfide bridge is, okay? It says here that the formation of a disulfide bridge is critical to the structure and function of many proteins. Well, hopefully you remember what a disulfide is. If you remember way back in the day, we talked about thiols briefly in the alcohols chapter. If I take, so this is a thiol, and the other one is obviously a thiol. If we oxidize that, we can produce what's called a disulfide. So this is a disulfide, what I have shown right here. And disulfide bridges, as we call them when we're dealing with peptides, are very important for the structure of many proteins. So you have to bear with me on my pronunciation of this amino acid. So I call it, sometimes I call it cysteine. If you go on YouTube or whatever, people call it cysteine. So this is cysteine. Okay, and here's another cysteine. Now this is one of the 20 naturally occurring amino acids. What if we had two of these cysteines in a peptide, the structure of a peptide? If we had them, in different places in a peptide, they could undergo an oxidation reaction to form a disulfide bridge. Now that's a covalent bond, isn't it? That's a really strong bond, okay? And that's going to provide some interesting biological significance to peptides and proteins. And I should point out that the molecule that's formed when you link the two cysteines together, this is called cysteine, okay? So not confusing or anything, cysteine. So we'll put here no E, or no second E, I guess, right? Cysteine has an E here, right? And cysteine doesn't have that first E there, okay? So we form that disulfide bridge and we form the cysteine molecule from two cysteines. There we go. Okay, well, those linkages, those disulfide bonds are really important. Like I said, they affect the 3D structure and thus the function of many proteins. Here's a couple examples of just, two proteins or two peptides. So we have this, peptide chain here. Okay, so that's neither here nor there. But you see that we have two cysteines, right? We have one here and one here. Now, again, we're not showing the entire structure of the amino acid just to keep things simple. We're just showing a part of it, but they're showing how there's a disulfide bridge formed between those two amino acids. And that's going to cause, this turn in the molecule, which again will have some kind of biological significance. Now, when it's between two cysteines that are in the same peptide chain, we call that an intrastrand disulfide bridge. And when it's between two different chains, we call that an interstrand disulfide bridge. All right. I just want to be doubly sure with you. One more thing is that this is an oxidation reaction. Okay. This is an oxidation. When I teach this reaction in nursing chemistry, I tell them oxidation in organic chemistry is the loss of hydrogens or the gain of oxygens. Okay. And since we're losing two hydrogens here, this is an oxidation reaction. All right. Here are some biologically relevant peptides. So what's the first one here? Leucine and methionine enkephalin. So these are two enkephalins, are both found in the brain, and they function in controlling pain. And you can see that these two peptides, leucine and methionine enkephalin, they only differ in one amino acid residue. Okay, so one amino acid is all they have. It's different between them. Okay, you look at the first four and they're identical. Another interesting peptide is bradykinin, which is a hormone that dilates blood vessels and acts as an anti-inflammatory agent. And you can see that if we were to write out the structure of bradykinin, which has a total of 9 amino acids, so we call it a nonapeptide. Okay, well, it's got all these amino acids. And again, when you see them written out in this chain here, you can assume that the N terminus is on the left-hand side and that the C terminus is on the right-hand side. So you can make that assumption when you see the molecule written out. A couple more. These are just some interesting peptides that are pointed out in our textbook. So vasopressin and oxytocin. Vasopressin is in the pituitary gland and has something to do with water in the kidneys and controls blood pressure. And oxytocin induces labor and stimulates milk production. Anyhow, you look at these two molecules, right? There's quite a bit of similarities between them, right? You look at this residue is the same and this one's the same, right? The only ones that are different are the ones that are highlighted in red. But you see how small differences in molecules can have huge differences in terms of their biological activity. Another thing I want to point out is that this is the C terminus. Now we think of a C terminus as ending with a carboxyl, like that, right? With ending with a carboxyl. But since they put that NH2 sticking off the end, this one here, what that tells you is that the C terminus is actually a primary amide. So it's like this. So the hydroxyl is replaced by an NH2 on the carboxyl. And the same thing applies here. All right. Well, with that in mind, let's try a problem where it says draw the structure of the following peptide. This is a tripeptide made of leucine, alanine, and glycine. And I'm going to show you the kind of quick way to draw these and to get the stereochemistry correct too. In fact, there is a skill builder in our textbook that you can look at. It goes through a problem where he asks you to draw a peptide and goes through all the steps. But I'll show you quickly how I would do it. The first thing you want to remember is you always want to follow this order: N, C, C, N, C, C, right? So on and so forth. The second thing that you can remember is that it goes NC carbonyl. So NC carbonyl. Okay, well, with that in mind, I think the easiest way to draw out a tripeptide is to start like this. So I go N, C, C. This one's going to be a carbonyl. Then I'm going to go up. N, C, C. This one's going to be a carbonyl. All right, I'm drawing a bond line structure here. An N, C, carbonyl. So I'm going like up and down, up and down, up and down, right? Because you see that this carbonyl is pointing down, this one's pointing down, but the one in the middle kind of is pointing up. So if you go up and down, and then I'm going to show you how to get the stereochemistry correct. Well, for a leucine, our side chain is an isobutyl. So isobutyl. I'm just going to write these down here to kind of keep track. For an alanine, it's a methyl. Okay, and for glycine, it's just a hydrogen. Remember, glycine is not chiral. Okay, well, with all that in mind, the next thing we're going to do is we're going to draw the protonated form of the N terminus, right? Remember, this is the N terminus. We're going to draw the carboxylate form of the C terminus. This is the C terminus. Okay, and if you're asking me, what if I didn't protonate this or leave this as the conjugate base of the I wouldn't care. Okay, as long as the structure is correct. Okay, it doesn't matter what pH you draw it at, really. Okay, so next we're going to put in the hydrogens on the nitrogens. So this nitrogen needs a hydrogen and this one needs a hydrogen. So all we have left to do is to fill in our R groups. We need an R group here, an R group here, and an R group here. Here's the easy way to remember it. Okay, if your R group is on the upside, so if your R group is on this direction, okay, R group is going to be drawn with a wedge. Okay, if your R group is on the downside like that, you're going to draw it with a dash. All right, and that's the easy way to get the chiral centers all correct. So since we have our isobutyl here, we're going to draw it as a wedge because the R group is pointing up. So we have our isobutyl group like that. So now we've covered our leucine. Next, we have the methyl group for our alanine. Remember, if the R group is pointing down, we're going to draw it as a dash. So we'll draw our methyl group like that. And then the last one, there's no chiral center. So we're just going to leave it as is. And now we've covered them all. And you see that we have NC carbonyl, right? That covers our leucine, right? Then you have NC carbonyl like that. That covers our alanine. And then the last one has NC carbonyl, okay? And that covers our glycine. And so we've put those 3 amino acid residues in the correct order. All right, there you go. So that's how to draw a tripeptide. You would use the exact same procedure if you want to draw any other kind of peptide. In fact, in the next question, you see that there's a peptide drawn over here. It's a pentapeptide. It says use 3 and 1 letter abbreviations. Using 3 and 1 letter abbreviations, show the sequence of amino acid residues in the following pentapeptide. Again, this is a problem where I would expect you to get out a cheat sheet or to look at the table in our book that has all the structures of the amino acids, and they're 3-letter and 1-letter abbreviations. Okay, so I would totally let you have that. Well, let's start by kind of isolating the 5 amino acids that are involved in this pentapeptide. So we have NC carbonyl. If we have an isobutyl, we looked at this in the last problem, it's a leucine. Then we have NC carbonyl here, we have a methyl, so that's an alanine. Then we have NC carbonyl here, we have a phenyl group on a CH2, so that's a phenylalanine. The next one is cysteine, okay, because we have a sulfhydryl group. And oops, did I go too far here? NC carbonyl. Yeah, let me fix that. NC carbonyl, like that. It's better. There we go. And then this one here is an aspartic acid. Okay, so again, we have a leucine here. We have an alanine here. We have a phenylalanine there. Here we have a cysteine. Okay, and here we have an aspartic acid. So aspartic acid. I don't know. Has anybody taken the time to try to memorize the 3-letter abbreviations? I don't know. Anyhow, so let's write them out. So it goes like this. Leucine, we use LEU. Alanine is ALA. Phenylalanine is CHE. Cysteine is CYS. And then aspartic acid is ASP. They're 1-letter abbreviations. The one phenylalanine is certainly not, phenylalanine and aspartic acid certainly are not intuitive. So leucine is an L, alanine is an A, phenylalanine is the letter F, okay? Cysteine is a C, and aspartic acid is D, like that. Again, I would provide some kind of cheat sheet for you if you wanted to, or if I asked you this kind of problem. Just kind of a funny story for you guys, for my students who are here today. A number of years ago, I gave a quiz at UCCS, you know, back in the pre-COVID days, right? It was a long time ago. And I gave them a sheet, I gave them the paper quiz. Then I collected all the paper quizzes, and then I gave them a bonus question, okay? Because they had already had the cheat sheet that they needed, because I told them you don't have to memorize the amino acids. But I said, I'm going to give you a bonus question, okay? Where I'm just going to draw an amino acid like that, and all you have to do is write down all of the R groups, the 20 R groups, and write down the names of each amino acid. And it was kind of funny because after I collected all the quizzes and started handing out the bonus question, as soon as I would hand it to them, they'd just hand it back to me and be like, I'm not doing it. I didn't take the time to do all that. Anyhow, again, for my students who are interested in taking biochemistry, it would be wise to memorize those now. Just get ahead of the game a little bit. Anyhow, if you think about the structure of a peptide, you know, if you have a peptide that has hundreds of amino acids all linked together, how do you figure out the structure, right? If you look at bradykinin, for example, it's a non-peptide that we saw a few slides ago. How did somebody determine the structure of that? Was it just by NMR? Well, if you think about the protons and the NMR there, a lot of them are going to have the same chemical shift, so that sounds like it would be difficult. I guess you could use mass spectrometry to some degree, you know, but one of the best ways to determine the structure of a peptide is to use what's called sequencing. And that is basically a technique where we isolate each amino acid residue one at a time, and then we analyze them one at a time, okay? And there's a couple of ways that we can sequence peptides, and one of those ways is to use what's called the Edmond degradation. So everybody needs to know the Edmond degradation. If you go back to the carbohydrates chapter, right, we learned the Vol degradation. Anyhow, this is something different, but it's in the same vein. It's what we're going to do is we're going to remove an amino acid, and this is important, from the N-terminus, so from the far right-hand side of the peptide, and we're going to remove it as this interesting intermediate called a phenylthiohydantoin intermediate, so PTH. Now, the phenylthiohydantoin derivative is analyzed to identify the amino acid. So here's what you do, okay? Here's your amino acid, or sorry, your peptide here. So this is the whole thing. Now, and you're like, oh, Mr. Dion, it just says peptide here. Okay, well, they're showing you the peptide, plus they're showing you the N-terminus, right? This is the N-terminus. And I know it's written on the right-hand side. It's backwards, isn't it? But anyhow, it's the way the author put it. So they have the peptide, they have the N-terminus. So here's your N-terminus right here. How are you going to figure out the structure of that amino acid, right? How do you figure out the identity of that R group? Well, the first thing you do is you treat it with this interesting compound here. So this is phenyl isothiocyanate. So phenyl isothiocyanate. Okay, so you treat it with that molecule. And then in the second step, you use trifluoroacetic acid, also known as TFA. Okay, we looked at the structure of TFA back in the carboxylic acid chapter. So first you treat it with phenyl isothiocyanate and then with trifluoroacetic acid. And what that does is it just removes the last residue, okay? Notice that I keep using the word residue. That's kind of the parlance that we use for each one of the amino acids in a peptide or protein. We don't just call it, oh, the amino acid. We say it's the residue, which means it's a portion of a peptide. Okay, so you remove that N-terminus residue, and then you end up with this interesting intermediate, which I'll never ask you to draw or anything like that. I would ask you to be able to recognize it if you see it in a police lineup, okay? The phenylthiohydantoin derivative, which is produced by a very interesting mechanism, which involves like a rearrangement, which I would never ask you to reproduce or anything like that. But the idea is that you form this intermediate, and whenever you form the PTH derivative, it's always going to have this part in common, right? But what part's going to differentiate them is going to be the R group. And so I'm not an expert in peptide sequencing, but I assume that this gets analyzed by mass spec, and then they would just look at the mass and say, okay, well, that's this amino acid. And what's interesting about this is that you can automate this process, and it can just keep, being repeated and repeated and repeated by some kind of instrument, and you can determine the structure of a peptide having up to about 50 residues. Now, what I understand, and I'm not an analytical chemist, but I guess that if you let this machine run, once you get up to 50 amino acids that you've burned off of this thing, I guess, it starts to get contaminated with all these different pieces, and then I suppose the spectrometry is not as accurate or something. I don't know. Anyhow, here's the mechanism for the Edmond degradation. I'll put this up here as an FYI. Okay, I'm not going to ask you the mechanism of the Edmond degradation. And you can see, if you look at it here, you got a nucleophilic attack. That's, something we all know, nucleophilic attack, some proton transfers and loss of leaving group, right? But then you have this rearrangement here, okay? Which, if you really have an inquiring mind, you can Google it or something, but I'm not going to ask you about that. Now, again, the Edmond degradation is great with peptides that are up to 50 amino acid residues. But what if we have a peptide that's got, that's bigger than that? Well, larger peptides, so having more than 50 amino acids, are going to be broken into smaller pieces or smaller chains using peptidases. Now, when you study biochemistry, you'll learn about peptidases, which hydrolyze peptide bonds, and you'll learn about the structures of peptidases. Now, we're just going to look at the names of a few peptidases. A given peptidase is going to selectively hydrolyze specific peptide bonds, and peptidases are, designed by nature. So, for example, here's one peptidase. It's called trypsin, and the name is a historical name. It doesn't tell you anything about, the enzyme. unlike we think like sucrase or something, or maltase or lactase, right? These are enzymes that hydrolyze disaccharides, for example. But trypsin cleaves the peptide bonds at the C terminus of arginine and lysine. So at the C terminus of ARG, arginine, and lysine, LYS. And you might notice something in common between lysine and arginine, and that is that they are both basic, right? They both have basic chains. And if you look at the structure of trypsin, and this is beyond the scope of our class, this is something you'll learn in biochemistry, but if you look at the pocket where the amino acid, either arginine or lysine, binds in the trypsin, it's called a serine protease, it's going to have an aspartic acid residue in it. So it's going to have, the aspartic acid like that. And that's going to form a salt bridge, right, with the protonated amine of the lysine, let's say. Okay, so anyhow, and you're going to have an interaction that's going to hold it in there. Anyhow, what you need to know is that if you see a peptide, for example, if you see this peptide here, you know that it's going to cleave on the C terminus side. Remember that the peptide goes NCC, right? So it's going to cleave on the right-hand side of the residue. So we have a lysine and an arginine in this molecule. So if we were to take this peptide, okay, right here, and you were to just throw trypsin at it, okay, what are you going to isolate? You're going to isolate these smaller peptides here, which are going to be easier to elucidate the structures of, either using an Edmond degradation or other techniques. Now, if you treat this peptide with trypsin, since it's going to break every time at the C terminus of an arginine or a lysine, if you look at the amino acids that are found on the end of these peptides, if it's not a lysine or an arginine, as in the case of this one here, it ends in a histidine, what does it tell you? It tells you that that must be the C terminus, right? I'll just write here C term. So again, if you were just given these three pieces here, you'd say, well, that part with the histidine, that must be the C terminus, and then you can work backwards from there. Now, if you're wondering, well, how would I work backwards from there? The answer is you would take that peptide and you would also treat it, in a fresh sample of it, you'd treat it with another protease. And chymotrypsin is a peptidase that catalyzes the hydrolysis of the carboxyl end of aromatic amino acids, these ones, phenylalanine, tyrosine, and tryptophan. If you look at the structures of the R groups of these three amino acids, they all have planar, flat, groups. So if we were to treat this peptide right here, the same peptide from the last slide, we end up hydrolyzing on the C terminus side of the phenylalanine, the tyrosine, and the tryptophan. Then we get different fragments this time, don't we? And we still have one that has the C terminus, and now we could work backwards using all of those fragments from the last slide and from this slide in order to elucidate the structure of the peptide. Let me show you how you would do that. Okay, I remember my first semester at UCCS doing this question with my students, and we burst out laughing because we, got the order wrong or something. Anyhow, so it says here, a peptide with 22 amino acid residues. So strap on your skates, Gordy. We got a lot of amino acids to put together. Is treated with trypsin to give 4 fragments. Remember that trypsin cleaves on the C terminus side of arginine and lysine to yield 6 fragments. While treatment with chymotrypsin yields 6 fragments, identify the sequence of the 22 amino acid residues in the starting peptide. Okay, so chymotrypsin, that cleaves on phenylalanine. So phenylalanine, and it cleaves on tyrosine, and it cleaves on tryptophan. So TRP. Okay, so now that we have all those, if you look at the first residues, we have arginine, lysine, arginine. Hey, look at this, we have a valine. Okay, if you look at the other set, okay, we are looking for phenylalanine, tyrosine, so tryptophan, tyrosine, phenylalanine, phenylalanine. Hey, look, I have a valine. So that means that the C terminus must have a valine. We're going to start with that valine, and we're going to work our way backwards. Right, so we can already start with this portion right here that I'm putting in this black box, right? Because this must be the C terminus. Okay, and the same thing would apply here, but there's only 2 residues here. So let's just get going. So we're going to have a valine, and then before that we'll have an alanine, then a phenylalanine, then a proline, okay, then a glycine. Okay, so let's cross that one out. So we've eliminated that, and we've eliminated that. Now you see that I have phenylalanine, proline, glycine. The only place I see that over here is right there, right? So I've already removed those ones. So before, I must have this piece, arginine, cysteine, and methionine, okay? Excuse my writing, it's a little bit messy here. So now I'm looking for arginine, methionine, and cysteine. I see it right here. I can cross those off. I've already got that done. Now I'm going to add this part, phenylalanine, histidine, tryptophan, ERP, like that. Okay, so I can cross this off. What else? The only place I have a tryptophan over here is right here. The only place I have a TRP. So I can go back from here, can't I? All right, I can go tryptophan. I can go backwards from there. So I've got my tryptophan, then I've got an arginine, so then I've got a leucine. Run out of space, so I'll go back over here. Then I have an isoleucine, ILE. Then I have my valine, my proline, then a lysine, like that. So I've gotten rid of all that. Then before my lysine, the only lysine that I have over here is right there. So before the lysine, there should be, so isoleucine, proline, valine, lysine, and then tyrosine. So tyrosine, and I'm right here right now. So I'm going backwards. Tyrosine, right? Cross that one off. Alanine, cross that one off. Valine, cross it off. Phenylalanine, done. And methionine, like that. And the proline, valine, isoleucine. So I've used up all of them. There you go. And if you count it up, that's 22 amino acids, and now they're in the correct order. So this is the order that they would come in. Again, this is my C terminus over here, and then this would be my N terminus over here. So that's how we use sequencing, using enzymes like trypsin and chymotrypsin in order to get some fragments. There are other enzymes that you can use to do the exact same thing, but these are the only ones that we look at in this chapter. All right, let's move on to 25.6, which deals with peptide synthesis. How do we go about? Yeah, it is a puzzle, isn't it? That's really all it is. It's nothing more than a puzzle. You're not expected to go anything further than that, Abby. That's about where the buck stops. Okay, so this is the last section. We got 25 minutes, so I'm going to try to get through all this peptide synthesis. To form a peptide bond, the N terminus of one molecule must be joined to the C terminus of another. So we're forming a peptide bond. Remember my first job in industry, a guy that I worked with said, how many ways are there to make peptide bonds? Seems like there's hundreds and hundreds of ways. But one popular way to make amide bonds is to use this reagent, dicyclohexylcarbodiimide, which we abbreviate DCC. It's a white solid. It has to be stored in a freezer, and I mean not a super cold freezer, just a freezer from a refrigerator. Anyhow, and it's really popular because why? Because it works really well. Now the mechanism, I'm going to go over this really quickly because I'm not going to ask you to do it. But if you want to look at the mechanism of the DCC coupling, feel free to do that. It's the kind of thing that would never be asked in ACS, so I'm not going to ask it on the quiz. Okay. Now let's get back to the peptide synthesis and the question, the real important question here. If we had two different amino acids, okay, and we were to treat them with dicyclohexylcarbodiimide, okay, so DCC, what would we end up? We'd actually end up with a mixture of 4 different compounds, wouldn't we? 4 different dipeptides, right? You'd have R2 and R2, R1 and R1, and then you'd have the different orders of the 2 R groups, right? Manifested in the first 2 compounds. So that's not very useful if you want to specifically couple this carboxyl to this, nitrogen. Is there a way to do that? Yeah, there is. Okay, I've done it many times myself. Okay, what we do is we protect the N terminus of the amino acid that we want the reaction to occur at the carboxyl, and we protect the C terminus of the reaction that we want to react on the amine. You remember protecting groups? We looked at these back in the alcohols chapter. Well, now you're going to learn a few new protecting groups that are popular in peptide synthesis. All right, so here's our strategy. Because after we've protected those 2 groups, we're going to specifically, aren't we? We're going to react that carboxyl with that amine, get our dipeptide, and then we're going to remove the protecting groups. So what do we need to learn next? We need to learn how to add protecting groups to a nitrogen, how to add a protecting group to a carboxyl, and then finally how to remove both of those new protecting groups that we're going to learn. Well, let's look at how we would do that. The first one is protecting an amino group as what's called a carbamate. Okay, sometimes people will pronounce it a carbamate or a carbamate. Anyhow, and to do that, we use this interesting compound that's shown right here. And you're like, wow, that's a pretty neat looking compound. This is called ditert-butyl. So, ditert-butyl dicarbonate. Okay. You probably also noticed that there's an anhydride here, right? This is an anhydride. And then this part here is a tert-butoxy, okay? It's a tert-butoxy, or a tert-butyl with an oxygen attached to it. So the way that we abbreviate this, since we have these 2 groups that are the same, right, with an anhydride in the middle, we call that BOC, Boc, subscript 2O, right? Okay, so another way of saying it is that this portion of the molecule here, this is a T-butoxycarbonyl. So that's the Boc portion. Okay. Another way that they write it sometimes is they actually put the T. So they'll put T-Boc 2O like that. Either one, and either one is fine. What I call it, I call it this. I call it Boc anhydride. In fact, if you talk to a chemist in a lab, that's what she or he will always call it. They call it Boc anhydride. So we treat it with this Boc anhydride, or ditert-butyl dicarbonate, which is just a white solid. Okay, so we treat that, and it does this interesting mechanism, which kind of looks like just a simple nucleophilic acyl substitution. But if you look after the nucleophilic attack, if you look at what's happening here, okay, you end up losing. Did I not put the mechanism here? Okay, you end up losing. Where am I here? Sorry, I guess is it not in my slides? Okay. Anyhow, I'll just move on. So anyhow, you protect it with Boc anhydride, and then you end up with a carbamate. Okay, so here's the shortened version of it right here. So you treat your amino acid with Boc anhydride, and you end up with a carbamate. So this is a new functional group, right? You guys know what an ester is, right? This is an ester. You all know what an amide is, right? This is an amide. This, if you have this, so if you have an oxygen like this, that's called a carbonate. And if you have an oxygen, carbonyl, and then a nitrogen like this, that's a carbamate, or carbamate. Okay, it's a new functional group you need to know. So you take the nitrogen of the N terminus, you protect it with Boc anhydride, you end up with a carbamate. Okay, and you can just abbreviate that. This structure right here, instead of drawing out the whole T-butoxycarbonyl, you could just write the nitrogen. So I'll put like this, and you could just write BOC. Okay, Boc, like that. Okay. All right. There we go. That's enough talking about Boc. Let's talk about Boc, right? Anyhow, Here's the mechanism for the installation of the Bach group. I won't ask you that mechanism. And then to remove the Bach, it's easily removed under acidic conditions using an acid like trifluoroacetic acid. And the acronym that we use for that is TFA, right? TFA. Everybody knows what acetic acid is, right? If you have CH3 carboxyl, this is acetic acid. And if you replace those three hydrogens, if you replace those with fluorine, CF3, right, like that, that's TFA. It's a much stronger acid than acetic acid. Okay, so we treat that with acetic acid and we remove that Bach group. The mechanism is shown here. And, you know, the driving force of this mechanism, which again, I won't ask you, is that you actually form two gases in the process. You form isobutylene, which is a gas, and you also drive off carbon dioxide. So, of course, based on Le Chatelier's principle, that's going to push the Bach removal forward. In fact, our book even says that the removal of Bach usually proceeds with 100% yield. So one of the, if you're having a bad, we used to say, if you're having a bad day in the lab, you know, nothing seems to be going your way, just get some Bach protected amino acid or peptide and just deprotect it and go sit at your computer and stare at the window or something for a few minutes, and then you'll be successful. Okay. Another way to protect an amino group of an amino acid is to use what's called an FMOC, which is a derivative of this molecule here, 9-fluorenyl methylchloroformate, and you make the FMOC. The mechanism for the FMOC installation is similar to that for the Bach protecting group, so just a nucleophilic acyl substitution. And then the deprotection of a Bach group is done using piperidine. So piperidine, and if you don't know what piperidine is, it's this molecule right here. Okay, so this is piperidine, just a liquid at room temperature. So you take the FMOC protected, right? Here's your amino acid. So this is the same thing as saying, you know, I've got my amino acid and I've got my FMOC group on it. You would just simply treat that with piperidine, okay? And what it does when it deprotonates this proton, or when it removes that proton right there, you get an aromatic resonance stabilized anion, and then it just falls apart, and it also liberates carbon dioxide, and that drives the deprotection to completion. So these are great reactions. You know, they work extremely well. All right, well, what about that carboxyl group? How are we going to protect that? Well, you guys know about esterification. If you take a carboxylic acid and you treat it with a catalytic amount of acid and an alcohol, and you remove water, right, you're going to end up producing an ester. The two most popular esters to form are going to be methyl esters. So a methyl ester would be OCH3, and then a benzyl ester. So a benzyl ester looks like this. You have the carbonyl, okay? Then you have CH2, and then an aromatic ring of phenyl. Hydrolysis can be used to deprotect the ester, to just break it apart, okay? Benzyl esters are very popular because they can be deprotonated or deprotected without using acidic or basic conditions. In fact, you can remove them using hydrogenation. Really popular reactions. Another reaction I've done Avogadro's number of times. Okay, if you want to remove a benzyl group, so again, another abbreviation would be like this. So if you have your carboxyl group like this, we write OBN for the benzyl. Okay, BN for benzyl. You would just break that off using hydrogenation. So just get a party balloon, fill it up with hydrogen, stir it, throw in your catalyst, go do something else, come back, and it's done. It's great, great chemistry. Another option is to treat it with HBr and acetic acid. Never done it, but I know it works. It must be substrate specific, you know, depending on the starting material, you might want to use HBr and acetic acid. And both work, and the book actually uses both. Seems to like both ways. So here's what you would do if we go, if we go back 10 minutes in time and we talked about how would you link, alanine and glycine together in this specific order, right? I want alanine to be my N terminus, and I want glycine to be my C terminus. Well, how would I do that? The first thing you would do is you'd protect the amino group of the alanine because you want the you want the carboxyl to react, okay? The same thing applies with the glycine. You protect the carboxyl group because you want the N terminus to react. Then you couple them together using dicyclohexylcarbodiamide or DCC. You make your dipeptide, and then you just deprotect it. Treatment with TFA remove the Bach, and then hydrolyze the methyl ester with sodium hydroxide. So that's just a saponification reaction, which is totally fine. What was I going to say about that? Yeah, that's good. Nothing more than that. Yeah, there we go. This method, the DCC coupling and deprotection, is not practical for forming a larger peptide. Well, I can tell you right now that if you want to make a small peptide, it's more than good enough. Okay, it works really, really well. But if you want to make big peptides, or then you're in trouble using that. It would take way too much time, because for every amino acid that you add, you have to do a protection, coupling, and then deprotection. So that's 3 reactions, 3 purifications. Really impractical. And so Merrifield developed a much more practical method for making, peptides, large peptides. It reduces the number of synthetic steps, and it's also very high yielding. And this is called solid phase synthesis, or solid phase peptide synthesis, SPPS for short. So if you're wondering, like, what would it be, solid phase? How am I synthesizing something in the solid phase? How are molecules going to move around in the solid phase? In general chemistry, they taught me that in a solid, the molecules or atoms, they don't move around, in a solid. Well, it's solid phase synthesis. So here, let me show you what's going on. The C-terminus of an N-protected amino acid, okay? Here's my N-protected amino acid right here. You see the C-terminus? It's a carboxylate, and then it's going to attach on the surface of a polymer. Now, I know we're going to look at polymers in the next chapter, but this polymer here is part of a big, big, big chain, which is going to be a totally insoluble molecule, right? This is a big hydrocarbon, and it's so big it's going to be totally insoluble in water. Okay, so it's literally going to be a solid in water, but they've designed this polymer to have these methylene chlorides on some of these aromatic rings. And so what's that going to do? The carboxylate is going to do an SN2, and then it's going to get attached to, you're going to attach the amino acid to the insoluble polymer. Okay, so after you've done this reaction, right, whatever salt that's produced, you can just wash it away, and then this is going to be a big hunk of solid left over. Okay, this is a solid. Now, normally, if you're like, what, it's just a big cube left over? No, no, no. It's usually on like little beads or something, like little tiny spheres that are left over. Okay, so then you can wash everything away. You've got your solid left over. Then what are you going to do? You're going to deprotect the box. So you treat it with TFA, right? You treat the whole polymer with TFA. TFA is not going to affect this big part at all. It's just going to remain. After you treated it with TFA, you're going to do another coupling. Okay, you rinse everything away, and now you've added another amino acid, right? You've added another residue. Now, obviously, here they're just showing the synthesis of a dipeptide, just two amino acids. But once it's done, say you added 100 different amino acids. Once the whole synthesis is done, all you would do is you treat it with HF, hydrofluoric acid, and then that's going to break this bond here. Okay, it's just going to knock it off the entire polymer, and then you can collect your product, and that's it. So the real advantage to solid phase peptide synthesis is the ease of purification. You put the polymers in the solution. When the reaction's done, you filter them off because they're insoluble. You throw them in the next reaction and keep going and going and going. And now they have synthesizers or automators, that do everything, leaving the polymer beads in the reaction vessel the whole time. Anyhow, I worked with a guy. I sound like I'm trying to, or anyhow, I worked with a guy who did this, for a number of years. He was a bench chemist, but they got him to do solid phase peptide synthesis. So they have instruments that are used, and anyhow, interesting stuff. And Merrifield won the Nobel Prize for this back in 1984. He synthesized ribonuclease, and it was really high yielding. It was like 17% after I don't know how many amino acids were added. And basically, the conclusion was the yield, the percent yield of every reaction was like 99% or something. So, all right. Excuse me. Let's see here. All right, this is the last question we'll look at. And if you're struggling with this, you could look at, so I've made a couple notes for myself here to tell my students. 2 things. Number 1, if you struggle with the Merrifield synthesis, there is a skill builder. So it's skill builder 25.6. It might be helpful for you. Another thing that you want to do when you're doing the Merrifield synthesis is assume, you're going to make the assumption you have Bach protected amino acids. Okay, so assume that you bought those from a distributor or you made them your own darn self. Okay, well, since the phenylalanine, this one over here, this is our C. This is our N-terminus over here. N-terminus here, and this is our C-terminus right here. Okay, well, where are we going to start? We're going to start right here, right? Because we're going to start with the C-terminus in the Merrifield synthesis. Let me show you how to lay this out. Okay, so first we're going to draw this Bach-protected phenylalanine. Let's start by doing that. And I might run out of space here on this slide, but whatever. We'll just go for it. So here's my carboxylate. This is my NH Bach. So this is phenylalanine, right? I have CH2PH. Okay. The way that you represent that polymer is you don't have to draw all those aromatic rings. You just draw the chlorine, the CH2, and then you write the word polymer. Polymer. Okay. Put that in a circle. That's the polymer. That's the whole thing. Remember, the first step is just a plain old SN2 reaction. So what are you going to end up with? Now, we're going to draw in a little different conformation. Let me show you. This is how it does it in the skill builder. And the reason why is because it shows you the N-terminus. Okay, we're going to write our Bach, and then we're going to have our nitrogen here. We're going to have this part attached to the polymer. Okay, like that. And then we're going to put in our R group, so CH2PH. Okay, so that's our phenylalanine attached to the polymer. All right, this part here, this is our phenylalanine, and it's just stuck on the polymer. So what's the next step going to be? We have to remove the Bach group so that we get the free amine. Okay, and then once we have the free amine, we can couple it to the Bach protected valine. So let me show you how you would do that. The first step is going to be TFA, trifluoroacetic acid. The second step is going to be to treat it with the Bach protected valine. So let's write that out. So we have Bach, NH, there, carbonyl like that. And I'm going to just draw the valine like this. Okay. There you go. And then, in order to save space here, so I'm just going to write the word polymer here. Okay. CH2. Then I'm going to have my phenylalanine. I'll put that in a circle. It's going to be attached to my valine. I'm kind of going up on an angle here because I'm running out of space. And then we're going to have our NH Bach. Okay, so from here on out, why don't we just use kind of shorthand? It just makes things a lot easier. So that we've already got the valine on. The next thing we need is the leucine. Remember, leucine has an isobutyl group. Okay, so first step is we're going to treat that with TFA. And the second step is we're going to treat that. Second step is we'll treat that with the Bach protected leucine. So Bach, NH, carboxyl. I'm drawing out the structure of all these amino acids. You don't have to do that in a Merrifield synthesis. Okay. Did I forget my coupling reagent? ECC. I think I did in the last step. So you have to have a coupling reagent, dicyclohexyl carbodiamide. Now we've got the polymer, CH2. We've got phenylalanine, valine, and we've got leucine. So phenylalanine, valine, and leucine. And then we're going to do the exact same thing again. So we're going to treat it with TFA. Then we're going to treat it with Bach, NH, is that carboxyl? I like drawing the carboxyls out. We have our phenylalanine. Don't forget the coupling agent, DCC. And then we end up with our final product. So we're going to add the phenylalanine to the end. And then the last step is going to be to treat that with, why don't I draw the whole thing? Yeah. So we'll put our polymer. And we've got 1, 2, 3, 4. So we got phenylalanine. We got valine. we got leucine, and we have another phenylalanine, and then that's going to have a Bach on the end of it, isn't it? It's going to have the nitrogen, hydrogen with a Bach. So then to get to the product, okay, first we're going to treat it with TFA. That's going to remove the Bach, and then we're going to treat it with HF, hydrofluoric acid, and that's going to remove it from the polymer, which I left my methylene out, so I'll fix that. There we go. And then we're going to have 1, 2, 3, 4, phenylalanine, leucine, valine, and phenylalanine. And there you go. That's the final product, like that. Merrifield synthesis. Beautiful stuff. We're going to skip sections 25.7 and 25.8. Again, if you're taking biochemistry in January or any other semester, I recommend reading through sections 25.7, which deals with protein structure, and then section 25.8, which deals with protein function.